Section 7.1, the properties of the normal distribution. Lesson objectives: graph a normal curve, state the properties of the normal curve, explain the role of area and the normal density function, describe the relationship between a normal random variable and a standard normal random variable. Lesson objective number 1. The area under the graph of a density function over an interval represents the probability of observing a value of the random variable in that interval. And what this is saying is there is a relationship between area and probability. And that's what we're going to look at in this lesson. Relative frequency histograms that are symmetric and bell-shaped are said to have the shape of a normal curve. If a continuous random variable is normally distributed or has a normal probability distribution, then a relative frequency histogram of the random variable has the shape of a normal curve. So here's an example. This is our random variable down here, x, and we see the center is the mean, and the points of inflection are mu minus sigma and mu plus sigma. So these are the two determining factors for any normal distribution. We need to know its mean and its standard deviation, sigma. This is the shorthand for writing a normal distribution. The n means it's normal. We put the mean first and then the standard deviation. So for these two cases here, they have the same standard deviation. They have different means. This would be for the pink one, and this is for the blue one. And as we look at these two down here, when you increase the standard deviation, there is more spread, and both are centered at 0. So the notation for the pink one would be 0, 1. The notation for the blue one would be 0, 2. Lesson objective number 2. These are properties for all normal distributions. It's symmetric about its mean, mu. Because the mean, the median, and the mode are all equal, there is a single peak, and the highest point occurs at x equals mu. It has inflection points at mu minus sigma and mu plus sigma. The area under the curve is 1. The area under the curve to the right of mu equals the area under the curve to the left of mu, which is a half. And that's because it is symmetric about mu, and the area under the curve is equal to 1. So a half plus a half makes 1. As x increases without bound, the graph approaches but never reaches the horizontal axis. As x decreases without bound, the graph approaches but never reaches the horizontal axis. So we say the tails never touch the x-axis. And the last one, the empirical rule, approximately 68% are within one standard deviation of the mean, mu. Approximately 95% are within 2 standard deviations of mu, and approximately 99.7% of the area under the curve is between 3 standard deviations above and below the mean. Let's look at this visually. Here we have 1 standard deviation, that's 68%. Here we're going 2 standard deviations above and below, and that's 95. And 3 standard deviations below is 99.7%. Lesson objective number 3. The data on the next slide represents the height in inches of a random sample of 50 2-year-old boys. Draw a histogram of the data using the lower class limit of the first class equal to 31.5 and a class width of 1. Do you think that the variable heights of 2-year-old boys is normally distributed? Here's the raw data. Let's look at the histogram. And from this histogram we see that the heights of 2-year-old males for this sample is bell-shaped and symmetric, so we would say it's normally distributed. On the next slide we have a normal density curve drawn over the histogram. How does the area of the rectangle corresponding to a height between 34.5 and 35.5 inches relate to the area under the curve between these two heights? This is the frequency distribution for the raw data, and we're looking at how many heights are in between 34.5 and 35.5. And as we can see here, if we add these percentage is up, it's equal to 20%. So if we look at the histogram with the normal curve, this is the bin for the interval 34.5 to 35.5, and we can see that this area of this rectangle, this bin, is 20%. So there is a relationship between area and probability. Area under a normal curve. Suppose that a random variable x is normally distributed with a mean mu and a standard deviation sigma. The area under the curve for any interval of values of that random variable x represents either the proportion of the population with the characteristic described by the interval of values, or the probability that a randomly selected individual from the population will have the characteristics described by the interval of values. Let's look at an example. The weights of giraffes are approximately normally distributed with a mean of 2,200 pounds and a standard deviation of 200. Draw a normal curve with the parameters labeled. Shade the area under the curve to the left of x equals 2,100 pounds. And last, suppose that the area under the normal curve to the left of 2,100 pounds is 0.3085. Provide 3 interpretations of this result. Okay, here's parts A and B. We have our curve. The mean is in the middle. And here we have 2,100. We're looking at the area to the left of 2,100. So this is shaded in. Part C. We can say that the proportion of giraffes whose weight is less than 2,100 pounds is 0.3085. We could also say that the probability that a randomly selected giraffe weighs less than 2,100 pounds is 0.0385. And we could also say the percentage of giraffes whose weight is less than 2,100 pounds is 30.85%. Lesson objective number 4. Standardizing a normal random variable. And this is going to be done by using z-score. So we take our random variable, we subtract the mean, mu, and we divide it by our standard deviation, sigma. This standard normal distribution has a mean of 0 and a standard deviation of 1. This is the notation for a standard normal. The mean is 0 and the standard deviation is 1. Here we have 3 different normal distributions with different means and different standard deviations. What the z-score does is it changes all these distributions into the standard normal. All these different means now will have the same mean as 0. All these different standard deviations now will be standardized into having a standard deviation of 1. If we look at the area under a normal curve with mean, mu, and standard deviation, sigma, once we change these values here, A and B, where A is less than B, into z-scores, what will happen is this area will be equal to this area. Let's look at an example. The heights of a pediatrician's 203-year-old female patients are approximately normal, with a mean of 38.72 inches and a standard deviation of 3.17 inches. We wish to illustrate that the area under the normal curve between 35 and 38 inches is equal to the area under the standard normal curve between the z-scores corresponding to the heights of 35 and 38 inches. So our first step is we compute the z-scores for the heights. So we're going to take our x, 35, minus the mean divided by standard deviation and round it to 2 decimal places. We get a negative 1.17. Our second z-score is going to be our x, 38, minus the mean divided by the standard deviation. Round it to 2 decimal places is a negative 0.23. And here's the visual. For x is 35, gives us a corresponding z-score of negative 1.17, and a height of 38 inches corresponds to a z-score of a negative 0.23. Okay, here's the readings and suggested problems. Thank Thanks for watching.